All right, so when we explored the ideas of Newtonian mechanics and the inertial frame of reference, so if you haven't yet watched that little mini lecture on the introduction to special relativity and that inertial frame of reference, we said that in that inertial frame, space and time are constant. And then we looked at different frames of reference, and we found that time is not constant, right? It's not absolute. That's what I mean by constant. So time dilation gave us this new appreciation that time is not absolute across different reference frames. And then if that were true, then neither was the idea of things happening simultaneous in one reference frame relative to another reference frame. And so if time isn't absolute, what about space? You could probably guess from the title that space, too, has a different view that we need to take when we think about it in terms of what we know about relativity. And so let's look at that. We're going to do a thought experiment, another great way to just sort of wrap our head around some of this stuff. And we're going to do an experiment where we think about traveling from Earth to Mars. Okay? And if I'm measuring the distance as if I'm on Earth or as if I'm on Mars, at these fixed locations, there's a certain distance between Earth and Mars. And we're going to call that L naught. Now, L naught, like T naught in our time dilation conversation, is what we call the proper length. Okay? It's the length measured as if we're at rest in a reference frame where the objects are at rest. So I'm in the reference frame of the Earth. Earth is at rest. Mars is at rest. The length between them is a certain L naught. Now, if I fly a ship from Earth to Mars, then how long it takes me to get to Mars is going to depend on how fast that ship is going and, of course, the length that it has to travel. But what if I view the trip from the perspective of the ship? Instead of viewing it from the perspective of Earth, what if I view it from the perspective of the ship? How does that change my trip? Well, we know from our conversations with time dilation that if I view the perspective of the ship, if I'm on the ship itself, my time is adjusted through our time dilation conversation. The time of this track is actually shorter. Go back and watch that video to kind of review that. But one way to think about it is, Earth is moving away relative to the ship, and Mars is coming towards me relative to the ship. So if the time is shorter in reference to the ship, and I'm traveling at a certain speed, then the length that I need to travel to get to Mars, well, that's going to be shorter too. So if we think about the length to get to Mars is going to be less than the length measured as if I were on Earth. And this is the phenomenon of length contraction. And so if we use our ideas about time dilation and that relationship between the speed of light and the speed of our moving reference frame, we find that our length contraction is equal to the proper length times the square root of 1 minus v squared over c squared, where that v is the speed of the reference frame. Square root. Boop. All right, so that ratio or that relationship, it should look familiar to us, right? We've seen that before. Now, let's define proper length, and we'll do an example. So again, proper length is the length. L naught is our proper length. And I caution you with that word. It doesn't mean true, it doesn't mean absolute, because what's true in one reference frame can look different than what is true in another reference frame. So I want you to make sure that you're not using proper as this is the right answer, the right length. But we need to define a reference point, right? And so the proper length is the length of the object as measured when the object is at rest. And another way to say that is it's measured as if you were doing the measurement, you are in the same reference frame. I'll say you, the measurer, are in the same reference frame. As the object. Okay? So if my object is the distance between Earth and Mars, and I measure it within that reference frame, that's my proper length. Okay? If I measure the distance moving on a spaceship, well, it's no longer at rest in the distance that I'm measuring it. So that will not be my proper length. Okay? And then again, our proper length is always longer than our contracted length. Hence the name contraction. Okay, let's do an example to kind of build on this idea. A little conceptual process part to it, and then just kind of getting familiar and comfortable with that relationship. All right, I'm going to erase as we read this question. So Dan is holding a 5-meter ladder, right? And he measures that ladder when he's stationary. And then suddenly Dan starts running, and he starts to run at a speed of, I've forgotten the actual number, 98% of the speed of light. What length is the ladder relative to Dan? And then what length is the ladder in reference to Carmen, who Dan's about to run by? Carmen's standing there on Earth, on the ground, and Dan is about to run by her. All right, let's look at the first part of the question. What is the length relative to Dan? Well, Dan is at rest relative to the ladder. He's running with the ladder. The ladder and him are in the same reference frame. So just like they were in the same reference frame when he was standing still, they're in the same reference frame when he's running. And so the length of the ladder is going to remain the same to Dan. It's going to be 5 meters long. All right? What about Carmen? If we are running with the ladder and the length is 5 meters long, that is the length in the reference frame of the ladder being at rest. So this 5 meters is our proper length when we consider looking at what Carmen is experiencing. And so we can use our relationship. So the length as measured by Carmen is going to be L naught times the square root of 1 minus v squared over c squared. And so we find that to be 5 times the square root of 1 minus, now we said that Dan is running at 98% of the speed of light, so that's 0.98 c over c. Remember, those are squared. The numerator and denominator are squared. And we find that to Carmen, the length of the ladder is 1 meter. Okay, so just sort of recognizing what's at my natural length, proper length, and then how do I utilize this length contraction, this idea of space being dependent on the reference frame. Oh, perfect timing. I'm just going to pop that off real quick. And we're going to stop the recording. You can't see it anymore because my camera does this goofy thing when that hits off. So this is quiet. Great job.